Okay, so hello everyone. My name is Leonardo. I'm a PhD student in State University of Campinas in Brazil, but I'm currently in a period of 6 months at CERN. I'm collaborating with Yukawa there, professor originally from Mainz. And today I'm going to talk, like the title says, about the neutrino decay in the cosmic neutrino background. So basically the idea is to use the cosmic neutrino background to probe if new physics exists or not. Sorry, I have to pick once here. And then... So the overview, I'm going first to talk about the detection of the cosmic neutrino background. Then I'm going to introduce the neutrino decay framework. I'm showing the preliminary results and then the conclusions. So I'm trying to answer the question of today's morning. Can we detect these non-relativistic neutrinos? Well, we surely hope so. And the idea is to use the neutrino capture in beta unstable nuclei. So we're using tritium atoms like this, which will capture neutrinos, non-relativistic neutrinos, and then this will induce a beta decay by this neutrino. So that's the basic idea of the detection. But then we also have this background that is the spontaneous beta decay. So when what we actually measure is this electron here, this outgoing electron. And in both cases, we have this final state electron. And in our case, this spontaneous beta decay spectrum is a background for our detection. So we have this continuous spectrum here, which is the beta decay spectrum. And here we have some peaks that correspond to the neutrino capture in the tritium. So let me first talk about the beta decay. So the beta decay spectrum here, as I said, is the main source of background. It follows this distribution here for the non-relativistic tail of the relativistic tail of the beta decay spectrum. We actually can learn a lot of nice stuff about this spectrum too. It's not just a background. So for example, we can learn about the neutrino hierarchy using the kink here in the beta decay spectrum. So we also can learn about the absolute neutrino mass, like Catherine is trying to do, for example. But the main topic of my talk will be the neutrino capture, so our signal from the CNB. So the neutrino from the CNB will be captured using this capture rate here, which is proportional to the PMNS matrix element. It's proportional to form factors, and by kinematic reasons, this capture rate will form a non-energetic peak here after the endpoint of the beta decay spectrum, which is proportional to the neutrino masses. So we have here, for example, two peaks corresponding to basically mu1 and mu2, where they are basically degenerate in mass. And then mu3 will form a second peak in a higher energy, and the opposite for the inverted order. Sorry? Okay, right? And okay, this cross section is very small. We have non-relativistic neutrinos, but we also have an enhancement factor by this clustering. So neutrinos non-relativistic, they tend to cluster because of gravity. This was calculated in all these works here. This is the general formula for this extra clustering of neutrinos near our galaxy, near our solar system. We are actually using this best fit here by this work from this is here, which also expands a little bit more in the range of energy that we are trying to use. Okay. And now let's go to the non-standard scenario. So inspired by the short baseline anomalies, one of the solutions for the short baseline anomalies that are basically exploring these two works here is to postulate that a neutral scalar eclipse which couples to neutrinos, and it couples to a sterile neutrino, of course, sterile neutrino state. And then the active neutrinos couple to this scalar cube via this sterile neutrino by the mixing of the mixing matrix, so the master, right? And the crucial observation that comes from this is that this interaction, this new interaction, induces neutrino decay. So if we think about this scalar field as being a propagator in the Feynman diagram, it will induce decay of the sterile neutrinos and the active neutrinos, among sterile neutrinos and active neutrinos. And this can happen in two ways. So it can actually happen that the heavy neutrino will decay into a lighter neutrino and a phi, and then this phi will further decay into an active neutrino, and then an antineutrino with these decay rates here, or it can happen via free body decays, like if this phi here is off shell, it's an off shell particle. Okay. So back to the spectrum that we observed with PTOLEMY. So the electron energy here. What does this mean in terms of the spectrum? So what can we observe? How can we observe this? The effect of this in the spectrum is that the higher mass peak will be missing in our spectrum. And not only that, but more events will be observed in the low energy peaks, that this heaviest neutrinos are decaying to the lighter ones. So this is the method that we are following to quantify this. So we solve this differential equation. So we propagate these neutrinos in time since they're decoupled from the original plasma until today's day. How they decay into this within this time frame. We then bin and smear the spectrum using the proposed detector range and sensitivity. So we have something like this in the spectrum, and here's how we expect it to be the 3+1 neutrino scenario with decay. We'll be missing these peaks, and the standard oscillation case. We then compare these two spectrum using a chi-square, also in a chi-square like this. Also taking into account systematic uncertainties in the true endpoint here of the beta decay spectrum. Also the overall normalization, the overall expected events for beta decay and overall expected events for the CNB. And this is the results that we find. So this for inverted ordering, we have a region here that corresponds basically to those two body decays, which are possible after the scalar mass is lighter than the mu3 mass, the heaviest mass. Sorry, this is inverted ordering, so mu1 and mu2. Here we have a region that grows linear in this log plane, which corresponds to the free body decays happening. Here for different regimes of the sterile neutrino mass. So we have a lighter neutrino mass. Basically, all the active neutrinos decay to this sterile neutrino. Here we have an intermediate regime of decay, where mu4 is produced by the heaviest states, but not by the lightest ones. And this is where mu4 is never produced. It's heavy, so it will never be a product of decay. And in this case, we see that the sensitivity decreases as we increase the lightest neutrino, the sterile neutrino mass. Sorry. This is because here we see a lot less events than we expect in the case of just three neutrinos with no decay. When we take a look, sorry.
Question here: should it be annually on the last annually or 100?
No, electron volts.
Wow.
Yes. In the case of normal ordering, sadly, we have no sensitivity to this decay, simply because we have a lot less statistics in the normal ordering case. But then, if we instead assume that the sterile neutrino is also produced in the early universe, together with the active neutrinos, so we have an initial proportion of mu4 being created in the universe too, and the energy is distributed among these four neutrinos. The original energy of these three species is redistributed into four neutrinos, we actually can see a little bit of the feature we see in the inverted ordering too. But this sounds a little bit boring. If we include additional exposure time, so for example, 10 years of exposure, then a lot more rich space, parameter space opens up. So we have a lot of different features here that I'll try to cover as many as possible. So first, we have this three-body decay region here, where the nu3 is produced by nu4 decay. And then this nu3 will further decay into nu1 and nu2. Sorry, I forgot to mention this is for normal ordering. And this gives us the highest sensitivity in our detector, since the high energy peak will be missing, and we'll have a lot of event counts in the low energy peak. This is a little bit suppressed in these two regions here, where we have a little less nu3 being produced in comparison to this region here, the body case. And this in turn leads to a little bit less overall event counts in our detector. So this reduces a little bit of sensitivity. We also have these regions here that we call combined peak, where nu1 and nu2 are produced, and they are present in our detector today. But we also have an accumulation of phi's. So not every phi will transform into neutrino, so we have a little bit less event counts. And then we have this resonant two-body decays here, where phi can further decay into neutrinos. So we actually have a little bit more, actually a lot more neutrino events than we have in this region here, where phi is produced and is stable in this case. Right. Then we have also this long peak, lattice neutrino peak, region, where only nu1 survives in our detector, and phi also accumulates in this case. So we have a little bit more sensitivity because we don't observe nu2 too, but we still don't have as much sensitivity as we have in this region. And we have this region where just sterile neutrino decays by three-body decays or by two-body decays. When this situation here mimics the original situation in the standard oscillation case and the standard feature of this new peak. So in this case, we have no sensitivity in experimental space. Finally, the last region is where no decay takes place. So since we divided the original energy into 4 species instead of 3, we have a little bit less counts in every peak, and then we have a little bit of sensitivity in this region where no decay occurs, but not that much. Finally, I just wanted to say that we are also starting to take a look at the sterile neutrino parameter space using this framework. So the parameter space of for delta and for 1 squared by the mixing angle squared. And we also expect to improve the sensitivity in this parameter space too, but this is still work in progress. I just wanted to highlight this. And now it's my summary. So the take-home message that I wanted to pass is that COB measurements can be good probes of new physics, especially because of this long time interval of the age of the universe while it's the neutrino is propagating. And this translates to a very low coupling that we can probe using this observable. And we expect a very rich parameter space full of different possibilities and novel, exciting perspectives in this field. And that's it. Thank you.
So when you in these parameter plots, when you say 2 sigma, 3 sigma, is this the discovery of the neutrino background aided by these decays, or is it an established discovery of the neutrino background and then you try to look for the decay.
Exactly, the second
Yeah.
case, yeah.
So basically, if you want to find a 3 sigma effect, you already assume that you have like a 5 sigma discovery of the phosphate neutrino.
Exactly, yeah, exactly. So we're comparing this picture where the neutrinos decay with the discovery of the single B.
Yeah. Okay. Other questions?
Thanks. Yeah, maybe relating to your question, as from my understanding, is PTOLEMY aiming for a discovery of the CNUB or setting limits?
He's aiming for discovery, yes.
Okay, wow. I mean, nothing is getting limits for overdensities for many orders of magnitude higher than it is, right? So it's super challenging to get the discovery.
There's an open sheet. I mean, just there's an 4.8.
I mean, over the mass. I mean, this, if I remember correctly, Campinas also doing something like this, right? They also give limits on CNUB over densities, and they are many orders of magnitudes away from the minimum.
Yes. In fact, I forgot to mention this during the presentation, but the main background is the beta decay spectrum, so it also overlaps with the peaks. So we have to have a very good energy resolution here to be able to isolate this peak here. So that's our main source of uncertainty. But PTOLEMY claims to reduce this uncertainty here to 50 milli-electron volts, which depending on the lightest neutrino mass, so here I'm assuming 10 milli-electron volts of lightest neutrino mass, you can actually see this peak in the spectrum and you can claim a discovery. But it all depends on the ratio of the lightest neutrino mass to your energy resolution.
And then I have a second question regarding the diversified. So you, of course, you need, if I remember correctly, a beta decaying isotope. But why do you need helium-3 if it's super allowed to decay, right? So it's super radioactive. Couldn't you choose something more calm?
To be honest, I don't know exactly the details of the experiments. So why did they choose the tritium? I'm not so certain.
How long? I think a couple of years, right? Lifetime of tritium.
I think so.
I guess there are also.
Actually, that's one that you really have value for weak interaction here, because otherwise you don't get anything absorption. Then you need something which is unstable.
Yeah, but there are many beta decaying.
Yes, but if the Q value is low, you have less beta decays, but also less probability for absorption.
Yeah, that's true. One of the advantages of tritium is the Q value to be low.
Okay, I see that there's a question also on Zoom here by Simone Costa. Simone, can you maybe unmute? We have to figure out if you.
Yes, I can. Can you hear me?
Can you say something?
Can you hear me? Hi, hello.
Can people unmute? Is that possible? Just give me a second. Maybe I have to change the output here. Can you ask your question?
Hi. Hey, Leonardo.
Yeah. Hello.
Okay. Thanks for your talk. I have a question about one of your last plots where you showed, I think, the number of neutrino family with time. And I was wondering if, okay, first of all, if it is like an effective number of families of neutrinos of relativistic or also non-relativistic. No, I
I
think
think it's 24.
one before. Yes, yes, one of these ones, because I can see that there are this black curve is something like between three or bigger than 3, and of which time we are talking, because I am a cosmologist, so I have seen some works that consider the introduction of an extra family of neutrinos trying to address the Hubble constant problem. So I was wondering if this is something that we could use also to try to address this problem, if it's something like before the Big Bang nucleosynthesis, or if we are talking like of now, of some decay that happens, and that now we have this number of family of neutrinos bigger than 3.
I see. Yeah, thanks for the question. Yes, so in this plot here, we are just distributing the energy density of the neutrinos instead of 3 species to 4. So it's still overall normalized to 3 in the neutrino decoupling time, but then it starts to grow in today's epoch. This is of course to avoid the unaffected limits during the early times of the universe. So what was your second question? I forgot. About the Hubble constants.
Yeah, if we could use this to address the Hubble tension.
I see. Yeah, so in principle, we can also, this plot was made considering the time of neutrino decoupling, so after BBN, just to be safe that we are not violating ineffective. But in principle, there are some mechanisms, like Joachim has a paper on that, of the neutrino secret interactions, where you can add a vector potential to the neutrino potential, to the neutrino evolution, sorry, which suppresses the sterile neutrino mixing angle, and so you can have a sterile neutrino in early times. But we wanted to be a bit more conservative here.
Okay. Okay.
In principle, you can also add this kind of scenarios in our analysis too. There's no problem on that.
Okay. Thank you.
Thank you.
Yeah, thanks, Simone. I think we should wrap it up now. So thank you very much, Leonardo, and everyone in the